This video is brought to you by thepuzzler.com. Welcome to the third session of the Puzzlers AMC 10 course. In today's session, we'll be looking at algebra on the AMC 10 test. In today's class, we'll be going through the following algebra topics: Vieta's formula, Vietas for bigger polynomials. We'll look at the polynomial remainder theorem, one of my personal favorites, the Simon's favorite factoring trig, or SFFT. We'll look at quadratics and their relation with like discriminants and functions. And then we'll look at sequences, including arithmetic sequences, geometric sequences, and a special type of geometric sequence called infinite geometric sequences. We'll also look at some algebraic tricks and manipulations, which includes commonly seen equations and formulas that you should know. And one special case that we'll look at is a Sophie-Germain's identity, which is a very special identity that has appeared on the AMC 10 a few times, and it can really make your work easier if you know what it is. With so much content to cover, let's get started. A polynomial is a function in one or more variables that consists of a sum of variables raised in non-negative integral powers and multiplied by coefficients. So an important thing to memorize or remember here is that it's non-negative. So it can be 0 or above. So 0 or above the powers, which means that the constant is included. For example, this general form of a polynomial, here you have all these terms where x is raised to any power from n to no power, but n is always positive, right? So n minus 1, n minus 2, all the way to n to the power of 0, which is just 1. It's always going to be an integral non-negative power. So for example, here's a polynomial, x cubed plus 3x squared y plus 3xy squared plus y cubed. So this is a polynomial in terms of x and y. A lot of the times you'll see polynomials in terms of just one variable, usually x. So for example, you could have 3x squared minus 5x plus 30, or just 60 itself is a polynomial because it's 60 times x to the power of 0, which is non-negative. So that's another example. Or maybe you could have 96x to the power of 87 minus 1. That's a polynomial as long as it's just a combination of non-negative integral powers of x and their coefficients. And the coefficients are usually specified by the problem, but there's some sort of limit to them. Either they're real, or they're rational, or they're integer coefficients, something like that. So I could technically have a polynomial that's square root of 3 times x to the power of 81 minus square root of 7 times x to the power of 60, and then plus 3 times x squared. So that's a polynomial. So you could have stuff like that. But one specific example of a polynomial is a quadratic. And a quadratic is of the form ax squared plus bx plus c, and a, b, and c are just the coefficients of the x term. So to find valid values of x that satisfy this equation, you use this formula right here. This is called the quadratic formula. In fact, I would suggest trying to prove this formula if you've never done that before. And it's pretty cool, not impossible to do, and it'll help you better memorize or understand this formula. So x is equal to negative b plus or minus, so there's usually two different answers, square root of b squared minus 4ac divided by 2a. And this stuff inside the square root, we call that the discriminant of the quadratic. If that discriminant is equal to 0, then the quadratic has a double repeated root, which means that it has one root, and that root is going to be repeated twice. So one example is x squared minus 6x plus 9. So you could use this, find it using the quadratic formula, or let's find the discriminant. So the discriminant would be b squared, so minus 6 squared, which is 36 minus 4 times c times a. So that's 0. So the actual solution to this, if we factor this as x minus 3 squared, is x equals 3. And you can see that there's two factors. So x equals 3 is a solution twice. And that happens because the discriminant is 0. If b squared minus 4ac is less than 0, then this right here is going to give us the imaginary number, so the quadratic has no real root. If b squared minus 4ac is greater than 0, then it'll give us a normal root, right? A positive version of the root that we'll take the first time around and a negative version. And that means that the quadratic has two real distinct roots. Okay, let's move on. Something that shows up a lot in AMC 10 algebra problems are the Vieta formulas. And Vieta's formulas for quadratics, here's what they state. So if you have a quadratic of this form with roots r1 and r2, then the sum of the roots is actually just equal to negative b over a. And the product of the roots is equal to c over a. So you can prove this. We won't do this in class, but if you write a factored quadratic as x minus r1 times x minus r2 times some coefficient k, and you actually multiply this out, you'll see where all these numbers come from. You'll see how this logically makes sense. But we won't do that in class. Instead, we'll look at the actual application of this. So let's do that. So what is the sum of the roots of this polynomial, this quadratic? We can notice that. And what is the product of the roots, and what is the nature of the roots? Okay, so by the nature of the roots, it's just asking, are they real roots, distinct roots? Well, what's up with the roots of this polynomial? So let's find the sum of the roots. So if we scroll back up, it says that the sum of the roots is equal to negative b over a. Okay, so here a is equal to 3, b is equal to negative 1, and c equals negative 4. So the sum of the roots is equal to negative b over a. Negative b over a, well, that's equal to 1 over the value of a, which is 1 over 3. So the sum of the roots is 1 over 3. What about the product of the roots? Product of the roots is just equal to c over a. C is equal to 4, or negative 4, and a is just equal to 3. So negative 4 over 3 is the product. Okay, to find the nature of the roots, we need to actually find the discriminant, which is b squared minus 4ac. And b squared minus 4ac, that gives us 1 minus 4 times the value of a is 3, and then times the value of c, which is negative 4. Okay, so that's going to give us 1 minus 4 times minus 4 is positive 16 times 3 is 48. So that's going to give us plus 48, which is 49. So that means that it's going to have two distinct roots that are real. Okay, that's good. Now let's double check our answer. We can do that here because we know how to find the roots of this. You can use a quadratic formula, or even simpler, you can factor it. If we factor this, we have 3x. So what would the terms be? There would be negative 4 and plus 3. Yeah, so it would be 3x minus 4 and then x plus 1. Let's just double check. Minus 4x plus 3x, that gives us minus x. 3x times x gives us 3x squared. Minus 4 times 1, that does give us minus 4. So we're good to go. So the roots are equal to 4/3 and negative 1. So this, the product of the roots is 4/3 times negative 1. Yep, we got that, negative 4/3. And then sum of the roots is 4/3 minus 3 over 3, which is 1/3. We also got that. And then finally, are the two roots distinct real roots? Yeah, they are. So that also we have. Okay, let's look at a problem from the 2005 AMC 12A. There are two values of a for which the equation 4x squared plus ax plus 8x plus 9 equals 0 has only one solution for x. What is the sum of these values of a? Okay, so important thing to notice here is we only have one solution for x. So that is what gives us like a bound on what our root must be. And we're given a lot of the coefficients, but more specifically, we're not given the coefficient of the x to the power 1 term, because we're given 8x plus 8, right? So I can rewrite this as 4x squared plus a plus 8, in parentheses, times x plus 9. Okay, so the product of the roots is equal to c over a. So the product of the roots, let's say the roots are r, and since the roots are the same, they're both r. since it says only one solution. All quadratics always have two solutions. It's just like we learned in the discriminant section. It's just that sometimes they're either double roots or not real roots. So it says only one solution for x. That happens when they're double real roots, which is when the discriminant is equal to 0. But let's play around with this. So we have r times r squared is equal to, from Vietas, 9 over 4. So r is equal to plus or minus 3 over 2. Okay, so now we know our roots. So now we can do x minus or plus, minus or plus, so plus or minus 3 over 2 squared. Now if we multiply this out, we're going to get the coefficient of the x squared term to be 1. But in the problem right here, the x squared coefficient is 4. So let's multiply by 4. You can do that without changing the actual roots. The roots are still the same. So if we do that, we get 4. So x plus, that would be 4x squared plus x times 3 halves times 2 times 4. Because that's the x plus y squared is equal to x squared plus 2xy plus y squared. So actually, instead of doing this in our head, let's multiply it out just so it's clear. So x plus 3 halves times x minus 3 halves and then times 4. And this is equal to 4 times x squared plus 3 half times this x, and this should be a plus. And then 3 halves times the other x. So that's going to be 3x times 4, which is 12x. And then what else? Then we have our final term, 9 over 4 times 4, which is 9. Okay. So what does that tell us? That tells us that this is one possible solution. But we could also have 4 times x minus 3 halves squared. So that wouldn't really change anything except for the sign of this term in the middle. This term would become 4x squared minus 12x plus 9. Okay, so 12, so it's plus or minus 12 is equal to a plus 8. So subtracting 8, we get 12 minus 8 is 4, and then minus 12 minus 8 is minus 20 is equal to a. It's asking for the sum of these values of a. So minus 20 plus 4, okay, that's just minus 16, and we can move on. There's other ways of doing this problem, and that's the cool thing about algebra. Sometimes there's other ways to manipulate this problem. And when you have time left on the test, you can always double check your answer. For example, you could do something here where you calculate the discriminant of this, and the discriminant must equal 0. So that would give you your two values for a. I didn't tackle it that way, but that's one equally acceptable way. Okay, let's look at this problem from the 2000 AMC 12. Let f be a function for which f of x over 3 is equal to x squared plus x plus 1. Find the sum of all values of z for which f of 3z is equal to 7. Okay, so this right here, this is confusing me. I'm used to seeing f of x is equal to something. Maybe I should convert it into that so that it's easier for me to remember what this function is doing. Let's say y is equal to x over 3. Okay, so then this would become f of y. And then this right here, this x term, well, if y is equal to x over 3, then multiplying both sides by 3, 3y equals x. So this becomes 3y squared. So 3y is in parentheses and then squared, plus 3y plus 1. Or f of y is equal to 9y squared plus 3y plus 1. Okay, so the problem is asking f of 3z is equal to 7. So what happens if we do y equals 3z? If y equals 3z, then we have f of 3z equals 9 times 3z squared plus 3 times 3z, which is 9z, plus 1. Or f of 3z is equal to 9 times 9 would be 81 z squared plus 9z plus 1. We know that 81z squared plus 9z plus 1. This is equal to 7. So 81z squared plus 9z minus 6 is equal to 0. Okay. Now we can divide all the terms by 3. So we get 27z squared. So 27 z squared plus 3z minus 2 is equal to 0. Can we factor this, or do we have to use a quadratic formula? 27 times negative 2 is negative 54. Are there any factors of negative 54 that have a difference of 3? Let's see. There's 27 to, there's 9 and 6. So if we have positive 9 and negative 6, that would give us a difference of positive 3. Or that would give us a sum of positive 3. So that would give us 27z squared plus 9. So that would be 3z plus 1. And then the other term would be 9z minus 2. Just double checking. 3z times 9z gives us 27z squared. And then 9z minus 6z gives us 3z. And then 1 times minus 2 gives us minus 2. And z is thus equal to negative 1/3 or 2 ninths. What is the problem asking for? It's asking for the sum of all values of z. So negative 1/3 plus 2 ninths, that's equal to negative 3 ninths plus 2 ninths, or negative 1/9, which is this option right here. So we can move on to the next problem. Let's now look at a problem from the 2005 AMC 12B. A quadratic equation x squared plus mx plus n has roots twice those of x squared plus px plus m. So straight off, I noticed that they have one variable in common. Maybe I'll use that somehow. And none of m, n, and p is 0. What is the value of n over p? Okay, so we know that the roots are twice those of this polynomial. Okay, so what does that tell us? Well, what is the relation between the roots, right? So the roots are twice. So the sum, the roots here are, let's say the roots are a and b, or let's call the roots of this a and b. Then the roots of this right here are 2a. Let me move up a bit. So this is 2a, and this is 2b. Okay, so I know that ab is equal to m. So now if I multiply 2a times 2b, that's going to give me n. And if you think about it, if we're doubling both of the roots, we're multiplying, each time we multiply a root, we're multiplying by times 2 what the original root was. So n over m is equal to 4. Reason being is because each of the roots is twice the previous root, and since we're taking the product, that's going to be a total of 4 times. So n over m is equal to 4. Okay, that takes us somewhere. Maybe now we could find a relation between m and p. Well, m to p, well, the roots right here is twice that. So when you take the sum of the roots, they're going to be twice the sum of the roots for p. So m over p is going to give us 2. And now we can figure this problem out. We know that n is equal to 4m by multiplying both sides by m. And then n over 4 is thus equal to m. So n over 4 p is equal to 2, or n over p is 8. And we can move on. So for this problem, we didn't actually use any Vietas to find the real root. We used Vietas to find the relation between two separate quadratics. Quite useful. Another application of Vietas from the 2003 AMC 10A. What is the sum of the reciprocals of the roots of the equation 2003 over 2004 times x plus 1 over x equals 0? Now, this isn't even a polynomial, because remember, polynomials must be x to the non-negative powers, and here we have x to the power of -1. So what does that mean? How do we go about solving this question? Well, let's multiply everything by a term of x. If we do that, stuff will start canceling out. We just have to make sure that x is not equal to 0. And we can do that by checking x equals 0 in this equation. Is it a solution? If x equals 0, this goes away, this is undefined and this is 1. So that's not even a solution. So x does not equal 0. Okay, so what does that tell us? That tells us that 2003 over 2004, x squared plus x plus 1, and then 0 times x, that's just still 0. And now we see how we could go about solving this problem. But wait a second, we're asked to find the reciprocals. I know how to find the sum of the roots, I know how to find the product of the roots. Didn't learn anything about finding the reciprocal. So we're asked to find if the roots are a and b. We're asked to find 1 over a plus 1 over b. Well, combining these two terms, that's just going to be b over ab plus a over ab, or a plus b over ab. Oh, wait a second. I know how to find the top. I know how to find the bottom. It's just the sum divided by the product. So it is something that I can find. So the top, a plus b, the sum of the roots, that's the coefficient of b, negative, so that's negative b over a. So negative 1 over a, which is 2003 over 2004. And this gives me negative 2004 over 2003. Okay, AB is going to be equal to C over A, or 1 over 2003 over 2004. These numbers are looking a bit nasty, but the choices don't look too complex, so let's hope that something will cancel out. So this will give us 2004 over 2003. Now, we're dividing this, so dividing by 2004 over 2003 is the same as multiplying by 2003 over 2004. So this would be negative 2004 over 2003 times 2003 over 2004. And now everything just cancels, and we're left with negative 1 as our answer. And we're done. So whenever you're given an algebra problem, sometimes they'll try to trick you by writing it in a form that you might not know about. So try to convert it to something that you do know how to solve. For example, quadratics for this case. And when we're asked to find the reciprocal, we found it in terms of something that we do know how to find, the sum and the product of the roots. Let's move on. Vieta's formula is quite simple for quadratics, but it also exists for higher polynomials. For a polynomial of the form f of x is equal to an times x to the power of n plus an minus 1 times x to the power of n minus 1 all the way to a1 times x plus a0, which is just a constant, with roots r1 all the way to rn, Vieta's formulas state that s1, or the sum of the root, is equal to minus 1 times an minus 1 over an. So this right here over this multiplied by negative 1. The sum of the roots taken 2 at a time is equal to the next coefficient, which is an minus 2, divided by an. Then the sum of the roots taken 3 at a time, that's going to be minus an minus 3 over an. So the minus positive minus pattern continues all the way to s of n, which is just the product of all the roots. And that's equal to the constant divided by the first term times negative 1 to the power of n. So these formulas, you'll see them all over the place in the AMC 10. And it's just best to remember that when the n roots are taken in groups of k, so for example, r1 through rn is taken in groups of 1, since we're taking one root at a time. And r1 through rn is taken in groups of n, since we're taking n roots at a time. This is equivalent to negative 1 to the power of k times n minus k over an. Let's look at a problem or two using these concepts. Here's a problem from the 2010 AMC 10A. The polynomial x cubed minus ax squared plus bx minus 2010 has 3 positive integer roots. What is the smallest possible value of a? Now, I want to preface solving this problem by saying that these problems are hard. They're from the last 5 of the AMC 10, and that's just due to the nature of Vieta's formulas for higher polynomials. You might see Vieta's formulas for quadratics in the first 20, but you'll never see it, or you'll rarely see it for higher polynomials, just because of the nature of the formulas. But let's try this problem. So they don't give us the value of this coefficient, and that's possible for 2 reasons. Either it's just to make the problem harder, right? If they gave us that information, it'd make it even easier. or it's just to tell us that this information might not even be necessary. And we'll find out what the correct answer to that is as we work through the problem. They do tell us, though, that it has 3 positive integer roots. That helps a lot because we're only given one coefficient, and this coefficient right here is 1. So we're only given 2 coefficients out of 4, so there's multiple solutions to this. But the fact that it's positive integer roots and we're asked to find the smallest possible value of a really limits down our scope. Okay, so the roots, let's say the roots are a, b, let's not use a, b, and c. Let's use, should we use r1, r2, r3? So the roots are equal to r1, r2, r3, and that is equal to 2010, right? Using Vietas, that's equal to 2010 because in a cubic, the last term will be negative over whatever, over the first term. And you can actually see that if you multiply out x minus r1 times x minus r2 times x minus r3, the last constant term will be r1, r2, r3, and since all 3 of them are negative, 3 negatives give us 1 negative. So that's where we get that from. Okay, so that's all good and so, but let's move on. What is the smallest possible value of a? So the 3 roots are positive integers, so they're positive integer factors of 2010. What is a equal to? A is just the sum of the roots, r1 plus r2 plus r3. Notice that's not negative a because we're given that the coefficient is negative a. So negative a times negative over 1, that's just going to be positive a. To minimize this, well, we just have to find the factors of 2010 that give us the minimum sum. What are the factors of 2010? Well, 2010 is equal to 201 times 10. 201 is equal to 3 times 60 plus, that's 180 plus 21. Okay, 67 times 2 times 5. So 2 times 3 times 5 times 67. So there's 8 factors, right? What does that tell us? We're asked to find the smallest possible value of a. So let's use a bit of logic. We know that 67 is the biggest factor by far. So if we combine 67 with any other factor, it's going to make it large unnecessarily, right? Because 67 times 5, that's going to give us 300 something. Instead, we could just split the 5 and the 67, and that would be what? That would give us only a sum of 72. So that tells us a general pattern of this problem. The 3 factors need to be as close as possible to each other. We don't want like one extreme. Like you don't want 2010 and then 1 and then 1. That's like the largest sum you could get. You want to distribute the terms. But you can't distribute the 67, so that's a factor of its own. Now you have 2 times 3 times 5. That's 15. But immediately I noticed that 2 times 3 is 6, and then 5 is equal to just 5. So we can distribute it like this. So now 67 plus 6 plus 5, that's going to give us 73 plus 5, or 78. So that gives us 78, and I know we can't do better. There's no other factor pairs that we have to look at because it's the least answer choice. So that's a gift from the MAA to us. So that really helps us know that this is the correct answer, and we can move on to the next problem. It's giveaway time. We'll be giving an Amazon gift card to 2 lucky winners this time. So that's going to go out to 2 random lucky winners who fill out the Google form this week for class number 3. And you can fill out the Google form by going to thepuzzler.com/amc-course-giveaway. The winners will be announced in the final week's video, which is next Monday. The winners of the last giveaway were Eric Yang and Anirudh Raj. You can email us to claim your prize. Don't forget to subscribe and like this video if you have not already. You doing that really gives us a boost in the YouTube algorithm, which helps us send this video out and make it reach even more people who need it. We'll give you about 30 seconds to enter the giveaway now, but it's okay if you can't do it right now. You can always do it right after the class is over. Let's now try a pretty hard problem from the AMC test. This problem is from the 2017 AMC 12A, and I believe it's number 23 on that test. For certain real numbers a, b, and c, the polynomial g of x is equal to x cubed plus ax squared plus x plus 10. and it has 3 distinct roots. So that might make a difference. So let's underline that. And each root of g of x is also a root of the polynomial f of x. What is f of 1? Okay, so it's not asking for what f of x is. It's just asking for f of 1. Well, f of 1, when you plug in 1 for x, all the terms are just going to equal to 1. All the x terms. So it's just going to be the sum of the coefficients, which is 1 right here, plus b plus 100 plus c. So if we find b and c, we're done. Maybe that's how we're going to tackle the problem, but I don't know for now. Let's assign some roots, though. Let's say the roots of this are r1, r2, r3. So let's make it a bit neater. Okay, so we have r1, r2, r3, and then this polynomial right here, this is a 4th degree polynomial. So all roots of g of x are going to be roots of this, because if it makes g of x 0, and then you plug, yeah, it tells you right here, each root of g of x is also a root of the polynomial. So then here we have r1, r2, r3. And then since it's the 4th degree, there has to be another root, so the root is going to be 4. Now, let's start using Vietas. So we are given from the offset that r1, r2, r3, r1, r2, r3 is going to be equal to negative 10. That's going to be equal to negative 10. Okay, what can we derive from Vietas right here? Product of all the roots, r1, r2, r3, r4. When you multiply them, that's going to give us positive c. Okay, what else do we have from Vietas? From this right here, we have r1 plus r2. So this is a two-wise sum, right? So you're taking 2 at a time. So that's going to be r1 plus r2. r1 times r2 plus r1 times r3 plus r2 times r3. And the coefficient of that is just equal to 1. So that's going to be positive 1. Okay. Now, from that first g of x, we also know that r1 plus r2 plus r3 is going to equal negative a. Okay, from this second f of x, we know that r1, r2. So you see a lot of r1s, r2s, and r3s. I mean, that should definitely help. Maybe we can manipulate the problem somehow to find those roots, or at least one of those roots. But taking the sum 3 times 3 pairs at a time, we get r1, r2, r3 plus r1, r2. So we can probably start noticing some patterns. We know that we know this term already from here, but let's just keep that in mind for now. We're given that r1, r2, and r4 plus r1, r3, r4, and then plus r2, r3, r4. This is equal to 100, and should it be negative or positive? So this term was negative. This term was positive. So this term right here is going to be negative. So this is negative 100. I don't think this is going to help, but it might. We'll find out. It seems to be very long, so if we somehow substitute this in, that's the only way this will help. But I don't know so far. So next, we know that the sum taken, this is 4 at a time, this is 3 at a time. Sum taken 2 at a time, 2 at a time from r1 to 4. That's going to give us b. So you don't have to write down all of them because we sort of know what it means. And then the sum of the roots individually, is going to equal r1 plus r2 plus r3 plus r4. And that's going to equal negative 1. Okay, so we can find a relation between a and r4 from the offset, because if we look at these equations, let me write r1, r2, let me rewrite that equation here, r1 plus r2 plus r3. This is equal to negative a. So if we subtract the second equation from the first equation, we would get r4 is equal to negative 1 minus a, which is just positive a, or a minus 1. So r4 is equal to a minus 1. Okay, So let's write that here. R4 is equal to a minus 1. Now, I know I said something about plugging this in here and here. We noticed that, so maybe let's try that. So then we would have negative 10. So that would be negative 10 plus the 3 terms. And I also noticed that all 3 of those terms have a R4 term in common. So that's going to give us R1, R2 plus R1, R3 plus R2, R3. And this is all equal to negative 100. So bringing the negative 10 onto the other side. And wait a second. This right here matches this expression right here. So I can replace this expression right here with just 1. It's equal to 1. And now we know what R4 is. So that's a cool thing about AMC 10 problems. Sometimes there's so many patterns, and that just simplifies the problem. So R4, if you add negative 10 to both sides, that's going to be negative 90. And since it's just equal to 1, not even some other number, it's just R4 equals negative 90. So then what is the fourth root? That is negative 90. Okay, that helps us a lot. That also tells us the value of a though. A minus 1 equals negative 90, so a is equal to negative 89. That's a weird, not nice number, but maybe that won't affect us. We'll see. Okay, so f of x, we found the fourth root, but what is f of x? F of x is equal to g of x, and then we're multiplying it by x minus the fourth root, which we now know what that is. That is g of x times x minus whatever the fourth root is, which we just figured out was negative 90. So if it's negative 90, then x minus negative 90, that's going to give us x plus 90. Okay. Can we use this information somehow? Well, I do realize the fact that we have the value of a, so we know g of x. We know what g of x is. So we're asked to find f of 1, and f of x is equal to this polynomial right here. What if I plug in 1 here? Then we get f of 1, let me zoom in a bit. F of 1 is equal to g of 1 times x plus 90, and x is 1, so 91. I know how to find g of 1 now. G of 1 is just plugging 1 into g of x, which I know what that is. So, oops, let's just zoom in back. So I know what that is. G of x, that if you plug in 1, that's just going to be the sum of the coefficients. So that's going to be 1 minus 89 plus 1 plus 10. That tells us 2 plus 10 is 12 minus 89. So 89 minus 12 gives us 77. So that would be negative 77. So this is simply just negative 77 times 91. Hopefully that's an answer choice, but we can check that. And it's a good sign that the answer is negative. So we have 77 times 91. What's the best way to calculate that? That would be 70 plus 7 times 91. Okay. How should we go about solving this problem? Actually, there's an even easier way to do it. Instead, let's just do 77 times 100 minus 10 plus 1, right? So 77 times 100, that's going to be 7,700. Oops. 7,700 minus 77 times 10, which is 770, which is 0, 10 here, 3, and here is 17 minus 7, 9, 6, 9, 3, 0, and then we're adding one last 77 here, which is 7007. And is that an answer choice? Well, yeah, we have to put our negative here. And is that our answer choice? Yep, it certainly is. And we've solved this problem. So this problem was a pretty long problem, right? And it's probably one of the harder AMC 10 problems you'll see relating to algebra. But what's important to realize for this problem is play around with the problem. Once you know the concepts, somehow those concepts will pop in. If you remember, my initial solution was to try and plug in and find the coefficients of this f of x. But at the end, I ended up finding the coefficients of g of x, right? I wrote f of x in a different way, and I found the fourth root using Vietas. So just, and we're gonna learn about all the important topics today, but just knowing all the important topics, after that, you just need to practice and try and play around with the problems, and eventually something will work out because the problems are made to be solved. Let's now move on to the next concept for today's class, the polynomial remainder theorem. It states that the remainder upon dividing any polynomial p of x by a linear polynomial x minus a, both with complex coefficients, is equal to p of a. So what is the remainder when x squared plus 2x plus 3 is divided by x plus 1? So you can easily solve this problem by using long division, but that's too long, right? So that would be easy to do, but it would be very computational. So instead, we can write x plus 1 as x minus negative 1. It's important to realize it says minus a and not positive a. And now, if you plug in negative 1 into this form, into this equation, you'd get negative 1 squared, which is 1, plus negative 1 times negative 2, negative 1 times positive 2, which is minus 2, and then negative 1 times, that's just plus 3. So this is plus 3. So 4 minus 2. That gives us a remainder of 2, and we didn't even need to actually do anything. And we're done. Let's look at some problems with polynomial remainders. Okay, let's try a problem from the 1950 AHSME test, which is basically an old version of the AMC test. When x to the power of 13 plus 1 is divided by x minus 1, the remainder is... Now you can use long division for this problem, but we know that if we just plug in 1 into this right here, we'll get the remainder. X to the power of 13, that's just 1 to the power of 13 plus 1, which is 2. And we're done. That's it. That's how easy that problem was. If 3x cubed minus 9x squared plus kx minus 12 is divisible by x minus 3, then it is also divisible by what of the 5 choices? This problem is also from the old version of the AMC. And here, we're going to find out something new. If we plug in 3 into this expression, let's call it p of x. So p of 3 is going to give us the remainder. But since it's divisible by x minus 3, the remainder is 0. So that tells us that if we plug in the value of 3 for x equals 3, then we should get 0 as our answer. Let's try that. 3 times 3 cubed, that's just 81, minus 9 times 3 squared, which is 9. So 9 times 9 is 81, plus k times x, which is 3k, minus 12 is equal to 0. So 3k minus 12, that's equal to 0, since 81 minus 81 cancels out, and k is thus equal to 4. Okay, so if k is equal to 4, what is our original cubic equal to? Well, our original cubic, that's equal to 3x cubed minus 9x squared plus 4x minus 12. So we notice the 4 to 12 and the 3 to 9 ratio. So we can factor out 3x squared from here to get x minus 3, and then factor out the 4 here to also get x minus 3. So this gives us 3x squared plus 4 times x minus 3. So this expression, we know it's already divisible by x minus 3 because the problem tells us. So we can, it's not that. 3x squared plus 4, is that one of the choices? Fortunately for us, it is. So that's our answer. So we move on to the next part of our class, commonly seen equations and identities. These are a must know, guys. Just knowing these really helps you when there's like questions that they're trying to throw you off. And just knowing them by heart really helps you make sure that you'll get those problems. I'll just quickly go over them. X plus y squared, this is one of the more common ones. That's equal to x squared plus 2xy plus y squared. X minus y squared, that's equal to x squared minus 2xy plus y squared. Now we have x plus y times x minus y, that's known as the difference of squares, and that's equal to x squared minus y squared. Now, this is just, you don't need to memorize this. This is more of just like foiling it out. If you just like expand the terms, x plus a times x plus b, that equals x squared plus a plus b times x plus ab. x plus y plus z squared. This is not something you should memorize, but it should be familiar to you when you see it. And that's equal to x squared plus y squared plus z squared plus 2xy plus 2yz plus 2zx. So you can see that it's pretty symmetric. Okay, x plus y cubed, that's equal to x cubed plus y cubed. You'll usually see this version. So x cubed plus y cubed plus 3x squared y plus 3xy cubed, y squared. And you might recognize those numbers from Pascal's triangle. And look at our CMP video for more context on that. That's where those coefficients come from. Same thing for this one, except it's going to be minus y cubed and minus 3x squared y. Sum of cubes, pretty important, x cubed plus y cubed. You can't really derive this on the test, so this is something that you need to know. X plus y is equal to x squared minus xy plus y squared. And then the negative version of that, x cubed minus y cubed equals x minus y times x squared plus xy plus y squared. And here's a special identity that is very helpful to know. So the Sophie-Germain identity. And this is quite rare on the AMC 10 test, but we'll look at a problem today where it actually showed up on the last 5 for the AMC 10. And that's quite tricky because that means that that problem wasn't really solvable using any other approach. Of course, there were other approaches, but using this identity, it was just much easier. So this identity states that a to the power 4 plus 4 times b to the power 4 is equal to a squared plus 2b squared plus 2ab times a squared plus 2b squared minus 2ab. Now we're going to look at some AMC 10 problems that don't necessarily correlate to these identities, just problems that we want to cover in today's class, and these identities might prove useful for us, except we will look at a problem that uses the Sophie-Germain identity, as I feel that's quite important for us to know for the test. So suppose that x and y are non-zero real numbers such that 3x plus y over x minus 3y gives us negative 2. What is the value of x plus 3y over 3x minus y? So this problem, not too hard, but just shows algebra on the test. The first approach might be to actually just expand, get x in terms of y, and then plug. Let's see if that works. So 3x plus y, multiply both sides by x minus 3y, so that gives us minus 2x, minus 3y times negative 2, that's 6y, or 5x equals 5y. Oh, wait a second, x is just equal to y, that makes it easier. So that means 4x over this right here is 2x equals 2. So that problem, it's just 2. So yeah, the algebra, they usually try not to make it too messy on the AMC 10, which only benefits us. Let's look at a problem from a more recent test, the 2020 AMC 10A. Real numbers x and y satisfy x plus y equals 4 and x times y equals negative 2. What is the value of x plus x cubed over y squared plus y cubed over x squared plus y? Okay, so how would we go about tackling this problem? Let's take a look. We probably want to combine terms in a like way so that we have less terms and then we can find it in terms of what we know. Let's start by exploring a bit. Let's do x plus y cubed over x squared plus x plus y, so plus y plus x cubed over y squared. Now, if we make them into common fractions for these two terms and these two terms, we'll get x cubed plus y cubed over x squared plus y cubed over x plus x squared, x cubed, sorry, over y squared. Okay, that's better than 4 terms. Now we have 2 terms. What if we make it into one term? If we make it into one term, we'd multiply x cubed plus y cubed times y squared plus x cubed times y cubed, or plus y cubed times x squared. This is over x squared, y squared. Okay, so we're sort of getting somewhere. We have that x squared plus y squared is equal to x cubed plus y cubed over x squared times y squared. But x squared times y squared is just xy squared. And we know that xy equals negative 2, so the bottom is negative 2 squared, or 4. Now, this right here is the sum of 2 cubes. And we know how to simplify that. So we can write that as x squared plus y squared. And then let's go back up to the sum of cubes formula. Right here, it's x plus y times x squared minus xy plus y squared. So we have, scrolling down, we have x plus y times x squared minus xy plus y squared. Okay, so we have one term now, but we don't know x squared plus y squared. But here's a cool type of manipulation that you can do to find that. X plus y squared equals, so x plus y squared equals x squared plus 2xy plus y squared. And we know this from our identity that we learned earlier. We know what x plus y is, so x plus y squared, x plus y is 4, so 4 squared is 16, is equal to x squared plus y squared. And we also know what xy is, so 2 times xy is negative 2, so 2 times negative 2, that gives us minus 4. So x squared plus y squared, that's just equal to 20. And now we can solve our problem. We scroll down, x squared plus y squared, that's 20. X plus y, that's 4. X squared plus y squared is 20 minus xy. Xy is negative 2, so 20 minus 2, which is 22, over 4. 4's cancel out. This is 220 times 2, or 440. And we're done. Okay, so that just shows how you can solve this problem. There's a few ways to solve this problem, but I think this way is the way that shows us the most identities being encompassed. Okay, what is the remainder when 2 to the power of 202 plus 202 is divided by 2 to the power of 101 plus 2 to the power of 51 plus 1? Let's take a look. So the first step in problems like this is to replace stuff, make it simpler. We see all these terms with 2 raised to these abnormally high powers. Let's replace it. Let's say x equals 2 to the power of 50. Well then, what is this right here? Then we're asked for the remainder when, what are we trying to find? We're asked for the remainder when 2 to the power of 202 plus 202 is divided by 2 to the power of 101 plus 2 to the power of 51 plus 1. So what is this in terms of x? Well, 2 to the power of 200 is x to the power of 4, and then we have 2 squared left, which is just 4. So 4x to the power of 4 plus 202 over 2 to the power of 101. Well, that's just 2x squared, because we have 2 to the power of 100, which is x squared, times 2, so 2x squared, plus, then we have an extra 2, and then x, plus 1. Wait a second, this seems to ring some sort of a bell for me. Let's scroll back up to our identities. Did we see something like this? Wait a second, it's right there. We did see something like this. In fact, I'm going to copy this right here and put it right here so that we can see it while we're solving. This is just a Sophie-Germain's identity. Well, in a way. If we let a equal 1 and b equal x, then this becomes 1 to the power of 4 plus 4x to the power of 4 is equal to 1 plus 2b squared would be x squared, so 2x squared plus 2 times 1 times x, which is 2x, times 1 plus 2x squared minus 2x. Dividing both sides by this expression right here, we notice that 1 plus 4x to the power of 4 over 2x squared plus 2x plus 1 is equal to 1 plus 2x squared minus 2x. So this right here is an integer. Because it's equal to this. If it's an integer, can we maybe rewrite this in such a way that we're using this identity? We actually can. We can write the top as 4x to the power 4 plus 1 over 2x squared plus 2x plus 1, because remember the denominators are the same here, plus the other 201 over 2x squared plus 2x plus 1. Now this right here we know is an integer. So we're just left with 201 as our remainder. Let's circle that and move to the next problem. Let's now look at one of my favorite algebra concepts that appears quite frequently on the AMC 10 test. Simon's favorite factoring trick, also known as SFFT. It's often used in Diophantine equations, which are just equations that have integer solutions, and we learned about that in our number theory class last week, where factoring is needed. So the most common form it appears is when there is a constant on one side of the equation and a product of variables with each of those variables in a linear term on the other side. Now that's just a bunch of words. Let's look at a practical example and you'll see what I'm talking about. So find all positive integers x, y such that x, y plus x plus y equals 20. So a problem like this, it's pretty hard to solve without being able to factor this term right here, right? Because whatever value you have for x, you always have a value for y. It's just possible that it might be an integer or not be an integer. So the way we tackle that is by noticing that if you have factorizations of the form x plus a times y plus b, this is equal to xy plus ay plus xb plus, so not xb, so bx plus ab. So given these coefficients a and b, you can add some other constant to this side to make it factor like this. And here's why that's useful. Here the coefficients are equal to 1 each. So, here the coefficients are equal to 1 each. So this would just factor as x plus 1 times y plus 1. And like I just said, it's useful because the constant term is going to be plus 1. So we have an extra plus 1 on the left side that we didn't have before. So we add the 1 on the right side too. And then it's validated. Now, x is an integer, y is an integer. So it's really easy to realize that x plus 1 and y plus 1 are both factors of 21. So x plus 1 and y plus 1, they're both factors of 21. We can just set them equal to factors and see if we get valid values for x and y. So it says find all positive integers. So all positive integers, that's anywhere from 1 to so on. So if you add 1 to each term, that's going to be anywhere from 2 to so on. Okay, so like if we do 1 and 21 here, so that x plus 1 equals 1 and y plus 1 equals 21, that wouldn't work because x cannot equal 0. So it has to equal at least 3 or 7 and 3. Okay, are there any other factors? No, 21, 1 doesn't work because y cannot equal 0. So x plus 1 is equal to 3, that gives us a solution 2, and y plus 1 is equal to 7, that gives us 6. And then we would just flip that for the next case since it's symmetric. So that would be 6, 2. Checking both of those, 2 times 6 plus 2 plus 6, that's 12 plus 8, which does give us 20, so it works. And same thing for the second one. So these are our two solutions. So it's quite important that you double check your solutions because usually for AMC problems, they'll have a certain restriction that you need to follow. Like the next problem. From the 2000 AMC 12, two different prime numbers between 4 and 18 are chosen. Okay, so different and their prime. When their sum is subtracted from their product, which of the following numbers could be obtained? Let's take a look. For this problem, let's assign some variables. We know that x and y, let's call our two primes x and y. We know that we're asked to find the product minus the sum, which is xy minus x minus y. Well, which of the following could be obtained? So we can factor this using Simon's favorite factoring trick as x minus 1 times y minus 1 plus 1. Or x minus y plus y minus 1. So we added an extra 1, so we need to subtract that 1. So minus 1. So now it says from 4 to 18. So all the primes from 4 to 18, they're odd primes. So an odd number right here and an odd number right here, right? And an odd number minus 1, that's going to give us an even number. So even times even minus 1. Well, that gives us some number to times 4, right? This is divisible by 4 since two even numbers multiplied together. That's going to be divisible by 4 minus 1. So it's equal to 3 mod 4, if you remember from last week's class on number theory. 3 mod 4, let's see, does that rule out any answer choices? Well, 21 is equal to 1 mod 4, 0 mod 4. This is 3 mod 4, so this is the potential option. This is 180 is even, so that doesn't even count. And then 231, that's also equal to, that doesn't work because 220 is divisible by 4, so then 10, 11, that's going to be, 231, that might work. Let's see, so 220 is divisible by 4, so then we have an extra 11, which is equal to 3 mod 4. So this one also works. 180 doesn't work because it's even. Okay, so we have two possible answers. So that's not enough to rule it out. Well, what's our maximum possible answer? Our maximum answer, that's going to be if the two primes are 17 and 13. So 17 and 13, if you multiply them out, you'll get 221. I did that using difference of squares, so 15 plus 2 times 15 minus 2, but you could just multiply it out. Minus 17 minus 13, that gives us 204 minus 13, which is 191. So the maximum is 191. This number is too high. So the only remaining option is 119, and we can confidently move on. Let's try a pretty hard problem from the 1987 AMC. Find 3 times x squared times y squared if x and y are integers such that y squared plus 3x squared y squared is equal to 30x squared plus 517. Okay, let's move all terms to the same side to see if that really gives us an idea on how to solve this problem, except for the constant. Let's keep it on this side. So we do minus 30x squared plus y squared plus 3x squared y squared is equal to 517. Now this looks awfully similar to the expression, to the Simon's favorite factoring trick expression, except instead of the degrees of x and y being 1, they're 2. And that's why I want to just emphasize, do not memorize this stuff. You want to understand it. Simon's favorite factoring trick is with one variable. This is with 2. That doesn't mean we can't use it here. If you understand that concept, of course we can use it here. We can say that minus 30x squared plus y squared plus 3x squared y squared, we can factor that as x squared, so something times x squared plus or minus something times y squared plus or minus something is equal to something, right? Very general, but instead of the terms being x and y, it'll just be x squared and y squared. So what is it going to be? So the coefficients right here, 3x squared y squared, the coefficient is 3. So when you're multiplying the x squared y term squared y squared term, it's going to be 3. And then the coefficient for the y squared term, that's 1. So this needs to be a 1 right here. Now the coefficient for the x squared term, that's going to be x squared times what is going to give us negative 30. If we put in a negative 30 here, does it work? Well, y squared minus 30x squared, and then plus, so y squared minus 30x squared, and then plus x squared y squared. No, that doesn't work. We have a 3x squared y squared term. What does that mean? Well, that means that instead of having a minus 30 here, what if we have a minus 10 here? And then we'd have a 3 here. Does this work? This gives us 3x squared y squared plus y squared minus 30x squared, and then we're adding in that extra minus 10. So this does work. So this shows how experimenting with Simon's favorite factoring trick can help us a bit. And since it does work, we have 517 here, and then we have to subtract that 10 to give us 507. Okay, so we have 3x squared plus 1 is equal to times y squared minus 10 is equal to 507. What is the prime factorization of 507? Well, 507, if you add up the digits, it's equal to 12. So it's divisible by at least 3. So if you divide it by 3, you get 1. So 20 divided by 3 gives us 6, 27, 169. I know that 169 is equal to 13 squared. So this equals 3 times 13 squared. Okay, so there's a high chance that there's only one possible value for x squared and y squared. There's usually always going to be two values for x and y since there's the positive and the negative square root. But there's a high chance there's only one value. So instead of trying to guess through it, let's try to use a bit of logic. Now, we know that the 3 term, 3x squared plus 1, well, x is an integer, so 3 times any integer is going to be divisible by 3. And then if you add 1 to that, that's not going to be divisible by 3. So the 3 cannot go here. So what if this is equal to 169? Then this right here would be equal to 3. If that's the case, then subtracting 1 here would be 168. And 168 divided by 3, what does that give us? That tells us that x squared, 168 divided by 3, that tells us that, so x squared is equal to 168 divided by 3, or 556. So x would be, we don't need to find x, we just need to find x squared. And then what if y squared minus 10 equals 3? Well, y squared equals 13. But both of these don't have a solution that's an integer. It says x and y are integers, so this doesn't work. So what if we try 13? And then this right here would be 13 times 3, which is 39. So 3x squared plus 1 equals 13. So 3x squared equals 12, or x squared equals 4. That does have a solution, x equals 2. So I'm feeling good about this. So y squared equals 49. That also has a solution, because y would just be equal to 7 or negative 7. So now we're asked to find 3 times 4 times 49, which gives us 12 times 49, which is 490, plus 98. I mean, not that, sorry. We have 12 times 49, which is 490, plus 98, which tells us that we have 8, 1 here. So our final answer is equal to 588. So that was a hard AMY problem, and they even tried to trick us by making us feel that we could somehow isolate this term. But if you just keep on doing the problem, trying different tricks, especially on the AMY when you have so much time for the problems, you'll finally find a way to crack through to the solution. Let's move on. Now, functions are a big part of the AMC 10 test, but they don't appear as just standalone stuff where you need to know something about just functional equations or stuff like that for the AMC 10. That does show up on the AMC 12, but not on the 10. So the concepts that we've learned about for the 10 that are enough to solve function problems, but let's try one. So 2019 AMC 12b, let f of x equal x squared times 1 minus x squared. What is the value of this sum? Okay, so very important thing that you have to realize is play around with the function. We know the theory, so now we just need to play around with it. Right here, I notice that the function, immediately I notice that the function is symmetric, right? If I plug in, not symmetric exactly, but if I plug in x or if I plug in 1 minus x, they both give the same answer. So f of x is equal to 1 minus x. F of 1 minus x. And looking at the choices, I immediately see how that comes into play. F of 1 over 2019 and f of 2018 over 2019. 1 over 2019 plus 2018 over 2019, they add up to 1. So subtracting them, since they add up to 1, they're both the same using this right here. So subtracting them from each other would just give us 0. Then the second term is subtracted, and then we're adding the second to last term. So that would also give us 0. And all the way to the middle, right? So our final answer, all the terms will cancel out. You do need to make sure that there's even number of terms, because otherwise there'll be one term left in the middle. But looking at the numbers, looking at them, they go from 1 to 2018. So there's an even number of terms. And then all the terms will cancel out. So that will just give us an answer of 0. So this question might look hard, might look like we need knowledge that we don't have. But really, it's quite simple. The answer was found using just playing around with the question. Okay, let's move on. Okay, let's move to the final part of today's class. Now we're running out of time, so we won't really be able to cover a lot of problems, but all the problems will be available in this week's handout and the homework problems for this week, which you can find the link to that in the video description below. So in algebra, an arithmetic sequence, sometimes called an arithmetic regression, is a sequence of numbers such that the difference between any two consecutive terms is constant. This constant is called the common difference of the sequence. For example, -3, 0, 3, 6 is an arithmetic sequence with common difference 3 and first term -3. And 99, 91, 83, 75 is an arithmetic sequence with common difference -8 and first term 99. However, 4, 2, 3, -4 is not an arithmetic sequence, and neither is 4, 16, 36, and 108 because the difference between consecutive terms varies. So to find the nth term of an arithmetic sequence, here's the formula, where a1 is just equal to the first term. So a1 is the first term. N is the number, just the number that you're trying to find. So if you're trying to find the fifth term, n would equal 5. And d is the common difference. So d is the common difference. The sum of an arithmetic sequence from the first term to the nth term is the sum of the first term plus the nth term times the number of terms there are divided by 2. If you have never seen this formula before, I would suggest trying to prove it. I'll give you a hint though. It's related to taking the average of the arithmetic sequence and multiplying it by the number of terms there are. A geometric sequence is a different type of sequence in which a sequence of numbers in which each term is a fixed multiple of the previous term. For example, 1, 2, 4, 8, 16, 32 is a geometric sequence because each term is twice the previous term. In this case, 2 is called the common ratio of the sequence. So to find the nth term of a geometric sequence, so an, it's equal to the first term times the ratio r, and then the n to the power of n minus 1. So n is just the term that you're trying to find. And then here's an important formula that you need to know for some problems, and if you don't know this formula, it can be very hard to figure out the solution. The sum of a geometric sequence is equal to the first term times the ratio to the power of n minus 1 and divided by r minus 1. And this is one of those formulas that just can't be derived during the test, so it's a good idea to memorize this. Now, something that's really cool with geometric sequences are infinite geometric sequences, in which there's an infinite number of terms. Now, usually you can't really do anything with them, but if the common ratio is small, which means that the absolute value is less than 1, the terms will start to approach 0 and the sum of the terms will approach a fixed limit. For example, if we have the sequence 1, 1/2, 1/4, 1/8, 1/16, and so on, you'll see that this will keep on going and eventually the terms will be very little. To find the sum of this, you use this formula, first term divided by 1 minus r. So the sum of this would be 1 over 1 minus 1/2, which is 1 over 1/2 or 2, which makes sense. This looks like it keeps on going towards 2, right? The sum is 1, then 1.5, then 1.75, and it's just hopping closer and closer to 2. A quick idea about how this formula is derived is if you look at the number right here, this formula right here, well, a to the power of 1, we can also write this as 1 minus r to the power of n over 1 minus r. If you multiply the top and the bottom by -1, you're not changing anything. Now, the absolute value of r is less than 1. So if you take this to the power of n, in this case, n is equal to infinity. So a number less than 1, if you just take it to the infinite power, like you just keep on taking its powers, it's going to become so small that it doesn't even matter. It's going to equal 0. So this right here is just equal to 0. So this gives us a times 1, which is just a, over 1 minus r, which is where the formula comes from. Okay, so there's a ton of problems that we wanted to look at for this topic, but like I already mentioned, that's going to be in the homework. Let's end the class with one hard problem from the AMC test. Here's a problem from the 2005 AMC number 2. An infinite geometric series has sum 2005. Okay, so the fact that the sum is equal to 2005 immediately tells us that for this problem, we're going to have a ratio that's less than 1, because otherwise we wouldn't be able to calculate the sum. A new series obtained by squaring each term of the original series has 10 times the sum of the original series. The common ratio of the original series is m over n, where m and n are relatively prime integers. Find m plus n. Okay, so this problem, the first series is, let's call it a, ar, ar squared, and so on. And we know that the sum of this is a over 1 minus r from our convergence formula, right? From our infinite geometric series formula. And this equals 2005. Now, if we were to square each term, we would get a squared, r squared, a squared r to the power of 4, and you can see the pattern. This is a geometric series with first term a squared and common ratio r squared. So this is 1 minus r squared. And this is 10 times 2005. So 20050. If we divide this right here by this, which we know is possible because a squared over 1 minus r squared can be written as 1 minus r times 1 plus r using difference of squares. If we multiply this by a over 1 minus r, what are we going to end up getting? Let's take a look. So this is equal to, and we're dividing this by a over 1 minus r, which is the same thing as multiplying by 1 minus r over a. And this 1a cancels out, 1 minus r cancels out with 1 minus r. And we're left with a over 1 plus r is equal to 20,050 over 2005, or 10, since we know that it's just 10 times the original sum. Okay, now we have two equations, two variables. Maybe we can just solve it that way. We know that a from this first equation, if we multiply both sides by 1 minus r, a is equal to 2005 minus 2005 r. And then from the second equation, a equals 10 plus 10r. Okay, so if it's both equal to a, we can set them equal to each other. We have 10 plus 10r equals 2005 minus 2005r. This is a simple problem for us to solve. 1995 equals 2015 r, or r equals 1995 over 2015. This, all the terms are divisible by 5. So 2000 divided by 5, I know that's 400. So this is 400 minus 1 on the top, 399, and then 400 plus 1 on the bottom, so 401. Or 403, since it's plus 50. Now, I know this cannot be simplified further because the difference between them is only 4. And what does that tell us? That means that if they're both simplified, if they both can be simplified, they're either divisible by like 1, 2, 3, or 4. And both the top and the bottom, the top is divisible by 3, the bottom is not divisible by 3, so 3 doesn't work. And both of them are odd, so they're not divisible by even numbers. So this is simplified. And since we're asked to find the sum, we do 399 plus 403. That would give us 2, 1 here, 802 as our final answer. Let's go back to the problem statement. Yep, it was just asking for the sum of the fraction, so we can write 809 and move on. Thank you for attending today's session. Homework is available at thepuzzler.com/courses/AMC-10-crash-course, and it consists of AMC problems containing topics in class. A lot of the stuff that we weren't able to cover in class today due to time constraints will be found in the handout for this week on that same exact link. Please don't forget to give this video a like if you have not already. If you have any questions, feel free to write them in the video comments and we'll try our best to get to them as quick as possible. Thank you, everyone.